Okay, so the recording has begun. So let's get into it. Make iterator. All right. So basically, how make iterator works is that it's being used by train iterator and test iterator, which calls make iterator. So make iterator is kind of an efficient way of getting the record reader data set iterator. So what happens to make iterator? What is passed to make iterator is train data. See, this is important for you to note because train data doesn't come from here. Train data comes from here, a file, right? So you have a static file, train data, train data. So this train data is actually set by this value after setup is called. So train data is created when setup is called. If you see carefully in the code, the first line is setup. So setup sets up train data and test data, and from there we start to do our calling of this function. So basically, train and test data is being passed into make iterator. So the data set is coming in. Then let's go into make iterator. Now, it's a bit difficult to do this if you think about it carefully. You know why? Because you have to work backwards. So you have this data set iterator, and that is what is being returned. And what is being pulled in is split, which is file split. So now we need to put it together in the sense, put it together backwards. So we got to begin by creating a new instance of new data record reader dataset iterator, because that's all we know, right? So if you look at this and you do a control P here, I think something is not exactly correct, but basically we need to create the record reader dataset iterator, and there is one option calling for a transform process. Even I took a while to realize why we needed the transform process, but then while I was looking at this, I saw that there was a schema here. All right. So basically, I realized that I needed to do some transform process, and that's why this three lines came about, because there's a schema. I could use the schema to create the table. I mean the features of the data set. So when I got this, then I realized that I could use the transform process record reader, which needed a record reader, and the transform process, which is this, plus the batch size, which is already defined up there. And 1 and 26 is because I already know the batch size and the column. All right. So when I was creating this, the only thing, this is purely to convert the label column to what is that, one hot encoding. All right, one hot encoding is actually to make it easier to compute. Because it's a way of converting, although the labels are already integers, but it creates a vector where it places a 1 where the label is situated. So this one hot encoding is actually useful, because here we've already converted label to a categorical. So this one is converting label to categorical. After converting it to categorical, we are converting it to a one hot encoding, just to improve the computing. All right. So what categorical does is that whenever it sees the label 0, it replaces it with 1. With the position, which is 0. 1 and so on and so forth. Then in one hot encoding, you get a vector of the size of you get a vector of the size of 26 that basically how it would look is something like this, where you have the array, the vector, and where if let's say the character is A, then it will be 1 and then all zeros. You have 26 zeros. So this format is called one hot encoding. That means it's able to see the entire label and see where this label is occurring. So that's what one hot encoding is done. So why I do this is, if I don't do this, I tend to get error in the array mapping. So that's why we needed to do the transform process and attach it to the transform process record reader. Did all of y'all get this? If you if you have any questions, please ask questions in your. I haven't said here. Save the file in the home folder, but for us, our PC, where we should put. Okay. I was using the list writable. Okay. Got error. Okay. Okay, because I think because we took a shortcut. I took a shortcut using transform process record reader, simply because I did a control P. I don't know why control P is not working on my computer now. Maybe because I got a program running. So I was able to do it this way, and so what's that? And then I think these parts you guys know how to do it. So this is what I was talking about. Transform process reader batch 1. This avocado thing is just taking forever to run, man. That's why I plan to, if I think I need to kill this, because I wanted to show you guys the processing. So because this is running, my thing is not able to show.
Sir, can you?
Yeah, Vimal?
Oh, right. Okay, sorry. Yeah. No, the sign language MNIST iterator, right? In the make iterator method, it says there on the top, this method instantiates an image record reader. So, like, is there a way to use the image record reader instead of the CSV one, or do we have to use CSV?
You have to use a CSV.
Oh, right. So that comment there saying use image record reader, that's
It's actually I did confront SkyMine on this, but they seem to say that this is an instance of image record reader. So CSV record reader is also an instance, and this one is completely misleading. That's why I told you yesterday that we needed to use a CSV record reader, simply because it's a CSV file. But what's it stored inside it is a image data.
Oh, okay, right.
Yeah, so that's why you needed to open or even look at the CSV file, because you see if it's a CSV file, right? See, it's a CSV file. It's not an image file. And if you open the image file, if I'm correct, I don't know why it's also 1 and not 0, because the label is in the first column. So I'm thinking this 1 is also the label, where the location of the label is. Okay, I think I will just kill off this for now.
Mr. Kanna,
Yeah.
isn't that for the label index it should be 0 since it is the first column?
Yeah, that's why I'm checking on that as well. Let's run it and have a look.
Yes, I keep getting the error as well.
This shape 96. Okay. So what sometimes is my problem is that this data may have already been downloaded. So what I need to do is go to the data directory and delete that folder and then try it again. So first what I'll do is I'll go to my folder. This is my desktop. I have deep learning and then data. This one here. So I'll just delete this whole thing. And then, why is it red now? Something is wrong. Again. Sometimes the file name of the sometimes it doesn't like when I put an extension like this. So what I have to do is I need to rename this because I'm not using that. And then okay, now I go back to my still says student master copy. We have the files. Where is the play button?
Mr. Kana, what does it mean when the num class is highlighted? What does?
Like this.
Yeah.
I'm not searching anything. Let me see. That means you never use the value. Oh, no, we are using the value. Test is here. Field can be converted to a local variable. Oh, it's saying that field can be converted to a local variable in the method. So they are saying you should bring it inside here. You should bring it inside here because you're not using it anywhere else. So like num classes being used here, but nowhere else. So they are saying it's just a help lah. Like for example, channel height and width.
We still can use it even outside.
Wait. No, it's just a recommendation, it's just a warning. But from what I see, the error, it says that field can be converted to a local variable. Convert a field to local variable in the main method, in the method main. More actions, right? So let's see what happened here. I'm still getting this error. Class path, okay. Class paths. CDLE full exam master class path default all looks okay. Project structure lambda 0.8 modules target source Java.
So I think there's a problem with the unzipping. Down there it says zip header is not found, probably not a zip file. Like a few of us had the same problem yesterday, so we had to manually download the files from the site. We couldn't use the method.
So it downloaded, but it didn't extract. Invalid zip.
So Vilma, where you put the file?
I put in the sign language MNIST zip file. It's the directories in the.
Yeah, it's only 4 kilobytes.
Yeah.
Just put inside.
No, I made 2 new folders for test and train, and then put the CSV files inside.
Oh, you not put into the exam files,
No, no, no.
Okay.
But I did not unzip it. I just put it just it is. I don't know.
Actually, if you look at the code, it needs to be unzipped and it needs to be in the raw format. So let's look for the URL. Oh man, today's class is a total bomb, man. See, it's a 30 megabyte file. You all can see, right, everything that I'm doing because I'm sharing the entire screen.
Yeah.
Okay, now I'm going to C drive, users, trainer. Oh, mistake. So these 2 files, these 2 must go in here. So when I go in here, I will see this and then the CSV file. Okay. Okay, now we're back to the same problem.
Mr. Kana,
Yeah.
what is happening? I don't understand.
Oh, what is happening is that you see here when we look at MNIST classifier, the first thing it does, it calls setup. Okay.
Okay.
Then what does setup do? Setup downloads the data. Okay, so the downloading part is not working.
All right.
So you have to do it manually. It downloaded the zip file. Can you turn off your microphone? Yeah, so basically it didn't download properly. So what it did was it downloaded the zip file, but the file is only 4 kilobyte. So it's useless. So I had to download it separately and then I extracted the file. So it created these files as well. PNG. Maybe I should put that into here. Okay, now let's look at this. Now there is an error. It's saying that the expected output columns must be equal to 28 by 28 by 1, but instead we got 96. So now this problem is definitely because of the transform process. The transform process that we are doing is not correct. So yeah, this is number of lines to skip. And the label index, this one should be 0, right? Okay, let's just look at the transform process. Okay, so the mistake was in the transform process. I just needed to do this one line. I thought it would improve the computing, but then it didn't. Okay, so now the this is generating what it's supposed to do. Do you follow? Okay, it stopped because of NaN, not a number. Not a number because it cannot have too many not a numbers. So that means it's not converging. So this NaN problem is because of my classifier. Okay, so we take one problem at a time. Do you all understand what I have done so far?
I don't get it.
Okay, so basically, when we do the transform process, we need to pass in the record reader and a transform process. Okay, you asked why this is 1, right? But by right it should be a 0. Okay, so it should be a 0 because the label index is the first column. And then the possible labels is 26. So this one is correct. Now the mistake was in here where the transform process, I needed to include the schema. if I don't include the schema, I am not able to tell Java what sort of column information it is. So I needed to create transform process so that I can put it inside my transform process record reader, which generates my record reader dataset iterator. So basically, when you do Control P, you can see that it's looking for. Okay, wait 1 second. So this generates a record reader. So I'm actually putting in a transform process, right, to generate a record reader. So new transform process creates a record reader, which is what is needed inside this method. So this method, if you look at the first column, it says record reader space record reader. That means the first variable should be a record reader. So what I'm doing is I am creating using a transform process here to include the record reader. I need to include this transform process in the record reader because only then there is the schema created for that CSV file. So I am doing 2-in-1, putting in the schema as the transform process and creating the record reader. If not, the record reader will be just empty. So you are right to say that. So once you've actually done that, when you do Control P, you will need to give it the batch size, which is already defined there, and then label index. It has to be 0, not 1. Right, I just wanted to put 1, and then if you run it, you will find there will be a mismatch in the output. All right, and then finally the number of possible labels. So this actually gives me my iterator. What I'm trying to do is I'm trying to work backwards. I already know my iterator is of type dataset iterator. All right, and
Mr. Kana, sorry, interrupt.
yeah.
Just now we go back to the MNIST classifier, the file, right? You re-downloaded.
Yeah.
Then you download in the deep learning 4J. Okay. Then we have data, right? Data then inside, because.
Okay, wait. Let me go to that folder.
Yeah.
So we are going to deep learning 4J data. MNIST.
Okay. So we must. So in the sign language MNIST, we must have this sign language MNIST /zip for them to read, because in the code it point us to this folder, correct?
Yeah, so I put it in here.
Okay, but in my folder, in this now you're showing, I got some other sign MNIST zip, but it's empty. Should I re-download again?
Yeah, that's what I showed you just now. I went to the website.
Yeah.
I put in the URL.
Yeah.
And I downloaded.
Because yesterday I downloaded, I thought the code want to read from our code, the exam folder. Then I put it in the resources. Is that right? It's not right.
Okay, by right, the code should download by itself.
Yeah.
So when I tried to download,
yeah.
I found that the file is only 4 kilobytes. So that means something happened with the download function, because the download function is right here.
Oh, okay.
See, it's right here. What is that? Class path. Download link. There, download file.
Download file, but it directs you to the URL.
This download link is the URL.
Download link is the URL. So we need to refer to the dataset helper.getProp values. And where do they get this from? Means the URL. It means go to the internet and download, right?
Yeah, so the helper files are inside here, inside the utilities.
Oh, okay.
So that's why it's called utilities dot. It's red because I think there's some error there that is not able to complete it. But basically, that's how they've designed the program. So your question is now, what is download link, right?
Yes. Wait. How actually the code read from it? If we don't read, then where should we put the directory? I'm quite confused here.
Actually, you don't have to be confused. You see, the path is given here. Data directory,
Okay.
sign mlist, sign mlist zip is the file name.
Yeah.
Okay, so this is the folder where it's called. So one is the data zip file. One is the class folder.
Yes.
So we have sign language mnist and then sign language mnist dash zip.
Yes, this is the directory. But
Yeah,
from
this is the
this,
directory.
the path, where do we get the path?
The path is coming from the properties,
From the
get prop
properties
values. So you have to open the properties file, which is the data set properties. So you see here, I already explained this before, right?
Yes, but I don't understand.
It's just a pointer only.
Yeah.
Because you see they are using get props value. So basically it's short form for get property values. So get property values will look into the get prop data set because this is something inside the data helper lah. The data helper you've already put the property file name, you see.
Okay.
So the property file name is pointing to this. So inside here there is a variable which is the download link. The download link is a value. So this is the value. So I just copied this value and I pasted it on the browser and I went here.
Okay.
Then
okay.
So
this value in the dataset properties is actually typed in by the coder.
What do you mean by type in by the everything is typed in by the coder?
Yes, means this one we put something here inside for the code to refer back.
Yes.
If you go outside.
Yeah. So if let's say if the file is now sitting it internally, you can actually put the path of the folder, like how they put the path of the folder here. So you can basically we do this because if in case the file path has changed, we don't have to change the code. We just change the location. Maybe one day Skyman will have their own repository. Then we don't have to use Google Drive, so they can just change it here.
Okay.
Okay. So now, so if everybody okay with the first part, I know it's a bit confusing, but this is the process of trial and error is the process of learning basically. I want you guys
no, I did the same thing yesterday, right? But I tested it out by trying to get labels from the train iterator, and it keeps returning null.
Sorry, what are you talking about? Which line?
No, not in the iterator itself, in the classifier. So you know that you get the chain and you put sign language mnist iterator up there. Sorry, up. All the way up. It's like at the chain when you first call the.
Is here what? Here.
No, up some more. Like right. Yeah. So after the chain iterator, right? So you get this, right? Okay. And then I tried to get labels to see whether it was properly getting the labels out, but it keeps returning null.
Oh, I see.
Yeah.
Okay, let's try it out. 1 second. Let me just because I haven't run this again. No. First, I want to go through the layer. everyone managed to do your layers here? Okay, let me start off with something a little bit more simple first. Let me try Adam. Let me try, let me remove this and put hello here. 5 by 5 is fine. Stride 3 1 by 1 is fine. Number of outputs, channels has to fit with your number of channels, which is 1. Then
Mr.
we have
Kana, Chop. What's the difference being put the activation above and put the activation in the layers?
when I put it up here, it automatically applies to everything.
Oh, okay.
So only unless I specifically assign like this, then it overrides that.
Oh, so it saves more time.
Yeah.
Okay.
Yeah.
So basically, the above few lines is applied on all the layers.
Yeah, correct.
Okay, okay.
So we have a dense layer. This one has to be ReLU. And then we have
Mr. Gana,
yeah.
why do we use the convolutional layer and subsampling? Because the dataset is in the CSV, right? So why do we need these two layers?
What we are doing here is we are doing a CNN.
CNN, okay.
CNN has got nothing to do whether it's CSV or whatever. We are just trying to capture features and classify the features.
Okay.
Yesterday, did you remember I told you what is the difference between a feed-forward network and a CNN? Izudin?
I can remember.
Huh?
I can remember the difference.
Sorry, you can't or you can?
Can. C-A-N.
Okay. The feed-forward neural network also captures features,
Okay.
but the CNN captures features and classifies at the same time.
Okay. Okay.
What is classify?
What? Classify mean it. We. It capture the feature and it automatically see. Saya nak cakap dia. It automatically arrange it to their assigned group.
Yeah, it automatically. What does the classifier do? Is actually it separates the data into different, let's say, clusters, so that we know that there are so many clusters in the data set. So that's what we are trying to do with this MNIST sign language. Okay.
Oh, okay.
So to answer your question, if you look at the images, if you go into the folder and you look at sign languages, you see the images appear like this. So we are trying to, these are all stored inside the CSV file, all these images. So we are trying to classify these images as different alphabets.
Okay.
So when you look at the problem, you must go deeper and open the files and look at what they're asking you to do. So basically inside this folder there's a CSV file.
Okay.
So inside the CSV file they have all these image pixel values in as rows.
Okay.
So now we are pulling in the pixel values and trying to find out how to classify this based on alphabets.
Okay.
Vimal, coming back to your problem, I think maybe the train didn't. Did you check the folder where the file are sitting in train? Do you see like 81 megabytes?
No, it's running and everything. It's just when I put the get labels, it's just returning null. Yeah.
Oh, okay.
So I put train.get labels, it's just null. So I was actually using that as a way to check whether it was getting the proper labels, but it kept getting null, 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 null. So I thought I was doing something wrong.
Oh, okay.
Yeah.
So you want to see the labels?
Yeah. Because in the dog breed iterator one, I think the custom model one, I tried the get labels and it just returned all the labels that it had, right? So beagle and all the other different types of dogs, but this one, it just keeps giving me null for the labels.
And you put it in here, is it? You put it like this?
No, I just put it on top right after I made the iterator all the way on top. Yeah. So right after the iterator, I just put train.get labels and yeah. So it's supposed to return a list of the labels, right? But it just keeps returning null for some reason.
So you see how I have changed the Elizabeth left the meeting. So how I've changed the activation layer and now we are not getting any ends. I see. Thanks, Annabelle. No, so it's not completed yet, and so when we run into this sort of issue, the train accuracy is 0.04. Yeah, you can share your screen. The problem is I don't want it to iterate so many times. So what I'm going to do is I'm going to reduce this to 1. And yeah, and then run it again. Let's just see if it gets the output correctly.
Did it manage to print the label? There, yeah, label equals null, yeah.
Data set iterator. maybe I'll try to solve it and share the line for you. I don't know why it's not printing. It should print that labels right now because it's already got the value. Let's see if there are. Anyway, let me just clarify with the rest of the team. Okay, so now since I've added a ReLU, I find that it's converging. I've changed the what is that? The train to just one. I get a good I get some accuracy. The thing about this programming is that it would take some time to figure out everything that is going on. So you need to be patient and try it and try this and try that. And when you understand something like what Vimal is doing, try to step out of the comfort zone and try to print out something, because you will always learn something new only if you try. In this case, that is the requirement. So it's printing out the train accuracy, and what is the test accuracy? Yeah, that so basically now what I'm doing right now is to get the thing working, and then we have to still improve our accuracy to our accuracy is still very low, all right? So we need to add a batch norm.
I think you have to type new. Is it? Oh,
Yeah. We need to change this to 2, to 3, to 4. Yeah, you can actually leave it like this. It will do some normalization. So what we do is here is we I pin this. Now I run it again. Okay, so can you all see how the code improved? So like here we had only like 0.2%, or this is actually 2% accuracy, and you see how the accuracy has changed.
Yes, we add batch normalization.
Okay, so now this is the secret, because they've already given you the answer here in this line. Okay, I'm going to take a break. I want you all to copy this code and run it on your own. Is that okay? I want you to make sure you understand what is going on here. So I will post this code in the CN. Sorry, I apologize. The class didn't go as planned, simply because I didn't realize that my data set needed to be downloaded again. But I wanted to take you all step by step and explain to you why we do certain things. It's just that the starting was a bit sketchy. Okay, for those who joined us late, right? I have shared the 2 bits of code. The first one, the one at the top, is the make iterator code, and then the second one is the what is that multi-layer configuration. All right, and then if you this is still not complete, yeah, because if you see, there is a huge difference between test and train. So you need to bring up the see, the train is actually very good, but the test is a bit low. So the question is asking us to bring it to how much? 85%. All right.
Sir, if you give it more data by increasing the number of epochs back to 10, would it be better, or?
Yeah, it should. It should improve, because we're only training it once.
Mr. Kana, where
Yeah.
do we put the dropout code? How to put?
Drop out. Which layer you want to drop out?
I don't know. That's why I asked.
Oh no, you just hit this.
Uh,
Hit drop out.
oh, okay, just like that lah.
Yeah. Then you put in your percentage.
Oh, okay. Can start from the first layer lah.
Don't put dropouts. I mean, you just put one dropout enough lah.
Means can put on the early layers or the late layers also okay.
Yeah.
But what's the recommendation usually?
Because the learning is very high, I
Yeah.
would put it in the early layers lah. You know, if you look at it starts off at 4. Then here, the later layers, the accuracy is quite. I mean, this is actually not accuracy. This is actually error rate. So the error rates are smaller. So I would put it in the front lah.
Okay. Look at the error rate lah. Okay.
Okay. So can I give you all like 20 minutes to go ahead and do this?
Yeah.
Any questions?
Mr. Kana, can I
Yeah.
look the CSV file directory? Because I download it manually, so I don't know how to set up the directory.
Okay, I'll show you. So you go to your your user folder. There'll be a deep learning for J, and then there's a data folder, right? Inside there, there's a MNIS sign language. Okay. Then there's another folder called sign language MNIS. Zip.
And then inside it, there's test and train.
Yes.
And inside it,
Inside
there's
it was the
CSV.
CSV file.
Okay, thank you.
Yeah, if ever you're confused, right? It's just that I know it's a bit difficult to see, but the path is actually here. The path is actually here. Sign language MNIS, then the dash zip, and then this is the other folder, the test folder. So this is telling it where to read the file. But if you go up here, it tells you the folder name. So this is the class folder. So always pay attention to the names that have been given. So this is the class folder. This is the zip file location.
So Mr. Kannan, now you give us the iterator and the classifier code, both. Or
Yeah.
only, okay.
Both. I gave you both.
Okay. Thanks.
No, the reason is I wanted you all to see the error rates change, right? By adding the activation function and then putting in the batch norm, you see how the thing flipped from 0.1 to 99%. And now I want you to bring up the testing. So it's like a balance. You got to bring down the training so the testing can come up. Okay, so I'll give you all 20 minutes. 10:20 now. I'll come back at 10:40. We have a lot to cover in terms of theory, so let's quickly get this done. So once you are done, can you just share in the Teams that you are done? Or should I create a Google Sheet for all of you all to put in your rates? So if you all want the link for the file to put in your test results, I'm going to share it now. So I created a sheet called sign language MNIST. So please put in your values there.
So do we have to test 10 iterations or just one?
No, the reason why I did one is because I wanted to get it to show you that it's already close to 99%. But
Right.
your work is not complete because you need to show that it's at least 85%. So you need to bring up the
Yeah.
So if you think about it, right, if you increase the epoch anymore, is it going to help the testing?
It will
Because
overfit.
yeah, because it's already 99% in terms of train accuracy.
Right. Okay.
So what Lai is doing is correct to introduce some dropouts, either that or reduce the number of outputs or inputs because it's learning too much. It's the same thing lah, doing dropouts and doing reducing the number of input outputs.
Right. Okay.
All right, so you don't have to change the number of epochs, but you got to change other parameters.
Mr. Kana. Mr. Kana. Mr. Kana. Hello.
Hello?
Mr. Kana. I think the prayer comes from Mr. Kana. Mr. Kana. Mr. Kana, are you there?
Are you having some problem with your IntelliJ and
Yeah, Mr. Kana, I want to ask question.
yes.
Actually, I want to share my screen.
Okay, hold on, hold on. I have to stop my screen, right?
Yes, you have to stop your screen.
Okay, done.
And share tray. Okay. Can you see my screen?
I can see LW only. Okay, yeah.
Okay. Now, okay, I cut and paste your code over here. Is
Yeah,
it correct?
yeah, correct.
I changed the iter to iterator, just the name. Is it okay?
Yeah, it's okay.
It's okay, Vic. Then I go back to, I don't need to run this, right? This is just
No, this
a
one cannot
supplement.
run.
This is a supplementary code to the classifier, correct?
Yeah.
Okay. Then I go to my code here. This is the code I wrote yesterday. You see whether any issue. Then I add on the dropout. I draw 20% first.
Okay.
Okay, my end out. I got about 6-7 layers like that. Then my first layer will be batch normalization. That's my second layer. Why I got this sampling? Okay.
Your convolution layer must be first.
Yeah. I just now I deleted the actually space. Just change this to
2, 3, 4, 5.
4, 5. Okay. So now I only one layer. Okay, this like this. Everything correct.
Where is your dropout? Any dropout? No dropout. Oh
My
God.
dropout is here. My first layer.
Okay.
This is my convolution layer.
You see, there's a mistake there. You got a convolution layer, batch norm, and then convolution again.
Oh,
You
okay.
can try that, but I don't.
But there one convolution, the batch norm is before the convolution layer, before it start.
Yeah,
Oh, okay.
you got two. The convolution layers are repeating.
So my this batch, I put in on layer 0. My batch. Where do I put my batch normalization?
Between your convolution layer and your subsampling layer. So basically,
Correct? What I did
it's
is correct.
as it is now.
Okay, it's correct. So
Yeah, so you have two convolution layers and then dense layer.
two sampling, then one dense layer, my output layer.
Yeah, correct.
Okay, so here should be nothing. Anything with the sign.
No,
My
just
build.
that all normal because that's just checking whether your network is null or not.
Okay, so now I play.
But it's going to take some time because you've got 10 epochs.
But it got some very fast. You see, I got this error message.
Okay.
We just read the blue one. Is it?
No, go up to the top.
Top.
Where it starts.
Yeah, this is the start.
Class path contains multiple host bindings.
And then
Can you go higher?
higher.
Line 66, is it?
What 66? Oh, 66. Line 66 is this one.
Okay, so it's a setup.
For setup, I didn't touch anything. It's at it is.
Go to setup in your iterator.
Iterator. Okay, set up. Okay. Set up.
Okay. Check if
The
the folder exists. Open your.
folder. I open the folder. I already deep learning project. This my home folder.
I can't see.
Oh, you can't see. Oh yeah. Hold on. You can't see. You can see. Okay. Okay, now I go to this.
Yeah, users.
Users. Then my name.
Yeah.
I go to
Deep learning project.
Okay.
Data.
Data. Okay. This one is the folder as it is. Then inside, I got my downloaded.
No, you must extract that file.
Extract outside or extract here?
You just extract in here.
Just extract in here. Okay. Extract.
What is the size of the file?
30 almost 30.
Extract all.
Extract all.
Okay, now open the MNIST file. Okay. Sorry, there's a mistake. Okay, can you click on it? Okay. So what you do? Okay. You see, there's data and then sign language MNIST, sign language MNIST, right?
Yeah. This one.
Yeah.
three.
The second sign language MNIST, right?
Yeah, this one.
No. The directory. You see, got data.
Test
No. The directory. The deep data. Sign
data.
language MNIST.
Yeah.
Okay. Click inside there.
Okay, inside there.
Okay. This folder.
Mm.
Sign language MNIST. Change the folder name to sign language MNIST-zip.
Oh.
-zip, not .zip.
Oh. Yeah. Like this.
Dash, not space.
Yeah.
Friend,
Yeah.
dash.
Dash lah. There's a dash.
I can't see.
Oh, you can't see? Okay.
Okay, never mind. Now try to run the code. Correct. Okay.
Run the code. Let me change the.
Can you pin it first? Can you pin the output?
How to pin?
Go down to the where the run is. You know the run at the bottom left. No, the below screen.
You could build.
No.
Run.
No. Go
There's a run.
see on the top there. There's a run.
Top, there's run. Here. Run this.
No. Bottom left, next to the file name, sign language MNIST, there's a run button. Scroll down, there's a pin.
I let you have control. Where is the control? It's too tough.
I think I have to request for
Okay.
control.
Okay, I allow already.
This.
What's that pin for?
So we can pin the output. You see here, I want you to see that it ran data load and stopped.
Okay.
So if you go back to your iterator, you will see that it printed out data load,
Yes.
then it failed. So this is an indication something happened after this. Okay. So that's how I know that this was the problem. So I pinned this. So now when I run it, it will create a new window. So this one still here.
Oh. Okay. So to compare the error message.
Yes, correct. So it's useful to use the pin. So now it's running. Let's see whether it executes beyond this or not.
Okay.
Okay, so it looks okay. Oh, not a number. So there means something wrong with the config. It will automatically exit when there are too many NANs.
Oh, what config? Each config.
Config is always your configuration.
Yeah.
So there's something wrong here.
Oh, so it must change.
Yeah.
But this is all processor only. What because NAA is not a number, right?
Yeah.
And I don't understand what this process can do to affect the numbers. Because the numbers is from the file, correct?
No. This is how you're configuring your network, ma.
Yes, correct.
So the network is not able to converge.
Oh, oh, this means it's not convergent.
Yeah lah.
Oh,
So I think the first thing you do is remove the Nestrov and just put Adam.
okay.
I stop control, huh?
Yes, yes. Okay, and share screen.
Clean up all the errors, because I think there's one extra bracket that's causing the error. Sorry, I stepped out just now to make a cup of coffee. Oh, very good score, Annabelle. Maybe you can share what you have done. Did you use 10 epochs or 1 epoch?
Well, Mr. Kana, I'm getting numbers already.
So I think the purpose of Nestrov, I don't know, I'm not very clear, because I think Nestrov is a bit too fast, I suppose. I don't know why. When I change it to Nestrov, I get that problem also.
But now I'm putting my learning rate as 0.00301. Then I found the convergence is very small because now it's 5, only a little. It goes down by very little. Should I increase the learning rate?
You are running 10 epochs or 1 epoch?
10.
Okay, that's going to take some time actually. So
Oh,
maybe you want to stop it, run it 1 epoch, and then make the changes so you can see you need to do this a few times to get your network to converge. So you need to look at the accuracy and make it converge.
So I have a question.
Yeah.
Right. So say you get a good test percentage, right, for 1 epoch, and then you run it for 10 epochs. Would it go down?
You see, the epochs has got nothing to do with the testing.
Yeah, but wouldn't it overfit if you run it for more epochs? No.
Yes, it would overfit if you run it for more epochs. But what you're trying to say is that the training set would be closely linked to the training set.
Yeah, but so it wouldn't affect test accuracy at all.
No. It would definitely would, because when you do so many epochs, you're actually training it over and over again based on the same data set. Remember, we want to have a general data set.
Yeah.
So if you actually look at your epochs, you will see that the accuracy, the error rate starts to plateau. Do you understand what I'm saying? Your error rate.
Yeah.
Yeah, once your error rate doesn't really improve very much, then it's good for you to stop your epochs.
Oh, okay. Right.
So it's not like you have to do it 10 or whatever. You have to do it so much that there is some learning at each cycle.
Yeah, but for like the exam when the default value is 10, so you have to make sure that you don't overfit by 10 epochs, right?
Yeah, correct.
Okay.
I'm not saying change the 10 to 1. I'm just saying that if it trains more, it will definitely overfit.
Right. Okay. Yeah. Thanks.
I always I advise my students to do this, but when you send it back, when you submit the answer, just put 10 and send back. Okay, because this is not inside the part where you're supposed to change any code. You're not supposed to change any code there.
Mr. Khan, are you sharing any screen? No, right?
No.
Oh, okay.
No, I want Annabelle to. Have you all updated your latest course?
I can't seem to get it above 80 something.
Is it above 85?
No, it's hovering around 80, 81.
Okay. Can we get Annabelle to share her screen? Annabelle, can we have a look at your network? How about you, Tang? Can you share your screen? It's okay. Just show us your configuration. Can you scroll up? L2 norm, batch normalize, wait init, then you got Adam, 3 decimal places, convolution layer, you got 20, or you're using an identity matrix there. And then move down, you got subpolling layer, and then you got your batch norm, and then you have another CNN with an identity. followed by sub-sampling, and then you have 500 in your fully connected ReLU layer. Okay, that's good. And then you have negative log likelihood, number of classes, softmax. Okay, and how many epochs did you run?
10 epoch.
One epoch.
10, 10.
Oh, 10 epochs. No, 9 epochs. And your accuracy is 1, and your test accuracy is 0.94. Ten epochs, okay. Oh, sorry, that was Annabelle. Thanks. So it looks like you tried a few combinations and you managed to get 10 epochs, and that's a very good score actually. So if you can replicate this in the exam, you're good to go.
Mr. Gana, I saw from Annabelle code the batch normalization put after subsampling layers. The batch normalization can put any layers after any layer.
Yeah, correct.
Oh, okay. Put on any other layers, will it affect the performance, the results?
I think it should, because
I try to understand how this batch normalization work.
okay. Do you remember why we are using batch normalization?
Yeah. Yeah.
Why?
Yeah.
Atif was the one who asked that question. What about?
Oh, batch normalization only happen only on that layer or batch. It doesn't affect any other layers.
It makes the neural network normalize the weights and biases because we have imbalanced classes. And we want to do it only on one layer.
Oh.
Because if we do it too many times, it becomes a regularizer. So if you regularize too much, you can cause overfitting.
Okay.
I can share an article. Okay, guys, I need to get started with the course. All right. So please remember how to do this. Remember how to practice for this. Remember how you wrote the code, and make notes for yourself. If you want, I can share some notes as well. So I'm going to share this file. Okay, this is a flow of code so that you understand how the code usually flows. So you first thing you do is you initialize. This one can either be inside your main function or it can be as a global function. Then the load data process takes place. This one could be the unzip, download and unzip. Then you got to prepare your file split until it becomes a dataset iterator and then a record reader dataset iterator. And then you do your whatever normalization. This is data normalization if required. Then you can do your multi-layer configuration. Okay, remember what values you're using, how many layers. All this is your creativity, this part here. And I want everyone to be different because I don't want them to think that y'all are copying. So try to come up with your own flavor of how you want to use all these hyperparameters, and then finally test and train. Okay, so every data science project will go through this flow. All right, so I'm going to share this file with you on CN. Okay, let's begin. Today we're going to do object detection. If you have not understood any of the parts before, for example, what is classification and what is feature extraction and how feature extraction is done, how linear regression is done, how logistic regression is done, what is the purpose of the activation function and all of that. If you don't have a good handle of it now, you're going to have a difficulty understanding these parts. That's my honest opinion. All right. So now we're going to learn more things about how all of these things are going to come together and used in different parts and used in different ways. So please bear with me. So we're going to begin by looking at what is object detection, what is all implemented in object detection. Now, there are many ways to do object detection, not necessarily YOLO is the only way, okay? And SSD has got one way of doing it, and then RCNN is another way of doing it. So they are all different ways of object detection. I'm telling you up front, what you need to know is why YOLO is good in certain cases, why SSD is good in certain cases, and why RCNN is better in certain cases. So you need to know it from a advantage, disadvantage point of view. All right, so let's begin. So this was done by my friend Wilson Chu. He was one of my lecturers when I was studying. So he went to Pavilion. He used his camera to take this video, and you see that it's already starting to draw a bounding box and put values around it, right? So basically, that's what we are going to learn. We're going to learn how it's going to draw a bounding box and then classify it and then give us a percentage of that classification. So all of these three things is happening at the same time. This is a groundbreaking step in computer vision because without having sensors, without having any sort of probing to the real world, we are just looking at the scene and quickly trying to understand what is happening. It's almost like a human being. The moment a human being sees this, they know it's a road, there's crossings, and then there's cars, there's a traffic light. Immediately it starts to figure out everything. So this was a very important step in computer vision because it was able to just look at the scene and then make inferences about it. Okay, but there are some problems that we will face. Okay, and the problems will be finding the object. Like human beings, we immediately, when we see a picture, we can immediately zoom into what is the object and what is the background. So to elaborate a little further, you also have problems where you have semantic segmentation, that means which is an object, which is not an object, and then you have instance segmentation, which is finding out how many of the similar objects are there. So if you break down this, there's three things that's happening. First is image classification that we did 2 days ago. How we do image classification, okay? Is done when we put a CNN where CNN is connected to a fully connected layer, it starts to classify. Today, we are going to do object detection, which is putting the image classification with the localizing of the object. All right, so there are many ways to do this. And we're going to look at the 3 or 4 different ways of doing this. And then next week, we are going to do semantic segmentation, instance segmentation, and face detection. All right, today we'll touch a little bit about a face, but the focus today is object detection. So in object detection, there are 2 problems. One is the localization of the object and the classification of the object. Now we are going to introduce a new data set called the Pascal VOC. All right, and we will measure the accuracy by mean, average, precision. This is another parameter that you will see coming up a lot. Just 1 minute, right? So that was Pascal VOC. And basically, deep neural networks was able to just escalate the speed of object detection. So basically, that's what this graph is talking about. So it's generally in the object detection space, we have bounding box and segmentation, and then finally, by taking it further beyond object detection is when we get to face detection. So they're all kind of related, all right? So this is just giving you the hierarchy of the object detection domain. Finally, we are talking about a generic object detection framework. So there are models that use region proposal. Region means within the image, we carve out regions that could have an object. So that is one way of doing it. After that, for each region, we find how many of it actually has an object. That is called the proposals that is generated for each region. So it's called region proposal. And then we combine everything and collapse into a single bounding box. That means we take the best fit bounding box for all the proposals that was given to us. All right. So this is the basic way of how we do object detection, right? So now we have done image classification, right? That actually looks at the boundaries within the image, and then it segments what's background, what's foreground. Now we want to know the localization. We want to know what is the bounding box that we can draw around that particular class, particular object. So what we do is so this is where the CNN takes over from the FNN. The FNN can extract features, but it doesn't classify it whether it's a car or a person. So when a CNN extracts the features, it actually starts to classify it. So this is what we mean by classification, right? So that's why a CNN has been much better in computer vision than a feed-forward network. Okay, now I have to qualify myself, right? This is one method of doing it, which is the YOLO method, where there are three things happening all at the same time. Now, the word YOLO means you only look once. That doesn't mean it doesn't go back and forth and generate the weights and biases. It does. It has to do that. Once it does that, the output can generate three things. The first one is a sigmoid. That means it's either a 1 or a 0. 1 if there is an object, 0 if there is no object. Okay? Then we need to do another one, which is linear regression, where we use the MSE as the loss function, or SSM actually, SSE, sum squared error loss function, to find out the best bounding box that fits the object, the best, because there are multiple bounding boxes. So we find the best bounding box. And what we do is we define the location of the bounding box by X and Y. The center is always X and Y, given the height and width. So this results with the bounding box that is best fitting the object. And finally, the class of the object, whether it's a car or background or person. All right, so three things happen, and this is for YOLO. So what happens when we generate the output or the prediction? It comes out in a 8x1 matrix like this. 8 because it's 8 here, but it depends on the number of classes, so it can grow. So the first value is showing whether there is an object. So in this case, it's 1 because there is an object, and bx, by is the center of the bounding box. B height and B width is the height and width of the bounding box. And these are percentages telling us what is the possible class of the bounding box. with the possible class of the object. So we get this sort of a matrix. Then now we understand that how we got this was whether there is a box or not. Now we look at how we do the bounding boxes. So the bounding boxes, one is the ground truth and one is the predicted. So there'll be many predicted, right? And then we correct it by using the loss function to find the best overlap. Then the intersect of union is the best overlap between where there is an object and where there is a bounding box. So basically, we already have, okay, so this one can be a bit confusing. You must understand that the image has already got the object in it, but the prediction is saying it's a bit away. So that is how we correct it, because the image has already got the bounding, the object already detected an object. Now we want to detect which bounding box is actually fitting the actual object. So this is how what we mean by checking with the ground truth. All right. So this is very unique in the sense that in an object detection, the object is already there in front of you. The concern is whether you've detected it correctly or not. So that is how we have this value called intersect of union that gives us the percentage. So the more the overlap, the higher the value, just like here. All right. So now what I mean by bounding boxes is it immediately splits the image into cells, and then it starts to check whether there is an object inside each cell. That is what the CNN is doing. So now it's saying that there's probably an object here, there's probably an object here, there's probably an object here, and there's probably an object here. So that is why you get 4 different bounding boxes. Does it make sense?
So, Mr. Kana, your yellow is a ground truth.
No, the yellow is the best possible bounding box that is overlapping all other bounding boxes.
Oh, okay.
No, you see, out of all my bounding boxes, this is my best bounding box.
Okay.
So that's how we get the best bounding box. In this case, we are then in the ground truth is telling me every time I do a weight change is based on my ground truth one. Because my weights and biases are changing, so my bounding box will move all over the place. So what I'm doing now is, after predicting all my different bounding boxes based on the ground truth, what is my best bounding box? And this method is called non-max suppression.
So the ground truth is decided by the user, is it? Or
No. The ground truth is actually telling me whether there is a box. There is a the ground truth is when I do the classification, right? In this image classification, I already know that there is an object here. So how am I going to know whether this you see there is always the ground truth and the prediction. If not, we cannot calculate how to move the weights and biases, right?
yeah. So the ground truth is when it just detects the object itself. So why doesn't it use the ground truth as the bounding box?
Okay, the reason is the ground truth doesn't have the coordinates. The ground truth doesn't have the actual center, because what we are doing now, we are going systematically cell by cell by cell to see where is the center that is the best bounding box. You see, we have a bounding box around this. We know there's an object here. We know there's an object here, but we don't know exactly where it is. So we need to break down the image into cells step by step, and then check which is the best bounding box that fits all of it. Because when I did my classification, I just looked at whether there is an object or not. Because the ground truth is not actually a box. It's actually the line, the boundary line that is going like this. Do you understand?
Okay, right, yeah.
So the classifier, when it looks at this, it looks at the boundary point. So it may even include this, but it knows that this is the object. So this is what the ground truth is, the actual ground truth. But it doesn't fit into a bounding box. So there is a difference between what is ground truth and what is bounding box. So in order for us to get the location of the best bounding box, we need to split the whole image one more time via cells and then check which bounding box best fits. Because I know now that this cell, this cell, this cell, this cell is overlapping the ground truth. So we have multiple regions that has the probability of having an object are selected. How do I know the probability of having an object is because of the ground truth? So now I take the bounding boxes that these ground truths, these cells have created. So that's why you have 1, 2, 3, 4 cells. Out of these 4 cells, I find the cell that has got the most overlap. So the yellow has got the most overlap of all the 4 boxes. By right, this one also should be an object, this also should be an object, this should be an object, this should be an object. So you get multiple bounding boxes generated. But of course, these won't have so much of an impact as opposed to the ones here. So basically what they are saying is that each cell will generate a bounding box. And this suppression of redundant bounding boxes is called non-max suppression. So now the best prediction, although I know the ground truth, the best prediction is the yellow box. So yellow is still a prediction. You see what I mean? That's why it's a bit confusing. If you already know the ground truth, why do we need to create a bounding box? But you need a bounding box to identify whether it's one object or two objects, and you will see that it becomes the norm, right? So this is what this is how we actually go step by step to find the best probable bounding box.
Mr. Kana,
Yeah.
why do you say that the bounding box that has high IOU is considered redundant? Because in your previous slide, it says high IOU is the best prediction.
Yeah, good point. I always thought high IOU is the one that, let me just check. The new slide deck also says the same thing. I honestly think there's an error in the slide deck, but I'll just check with SkyMine. I'll just send him a text right now. Okay, let's take this for the truth right now because it says excellent and IOU is the high score. I'm also thinking that this is correct and I think that this line is wrong. It should be, has a low IOU, low overlapping, are considered redundant and will be removed. So this is an example of the output when there is an object. So we consider face detection similar to object detection. So when you extract the features and then it does a convolution, finally it classifies whether it is an object or not an object. So basically this is what the sliding window detection does. Big downside to sliding window detection is the computational cost, which is very extensive since we have a lot of windows. The solution to do that in a sliding window window detection computed convolutionally. This is taking you to the next. So they are taking you from a fully connected layer into convolution layers. All right. And basically, this is a flat 400 by 1. This is a three-dimensional 1 by 1 by 400, which is what we call a convolution layer. So this is the change that they do to convert from a fully connected layer to convolution layer. Okay, the reason why they put FC, the implementation of the convolution is using a fully connected layer. It's just that the dimensions of the layers have changed.
Mr.
Right?
Kana,
Yeah.
what is the fully connected layer? What do you mean by fully connected layer?
In another words, the dense layer that we use in our programming. Hello?
Yes, I can hear you.
Yeah, the dense layer. Remember the dense layer?
Yes.
That's a fully connected layer.
This dense layer.
Yeah.
Dense layer. This means the activation layer.
Correct.
The dense layer only have activation.
The activation happens in every layer. It's just that it's not a convolution layer, it's not a subsampling layer, it's not the output layer, it's a fully connected layer. That means every input is connected to the output and it's got an activation function in it. That is what we mean by a convolution layer. That means we have the convolution and then we have the fully connected layer and then it becomes a classifier.
So
when you don't have the fully connected layer or the dense layer at the end, it doesn't classify. It just gives you the probability. That's why we say a fully connected layer, a feed-forward network can only extract features, but it doesn't classify the features. Meaning, when I extract the nose, the ear, the eyes, it doesn't classify it as different features. It just looks for whether the features exist or not. Remember, the classification is either 0 or 1. There's a subtle difference in terminology. Okay, basically, if I were to give it another set of pictures with the same ear of a dog, let's say if I give it a picture of a tiger, oh sorry, a lion, right? It cannot in a CNN it can match the ear of a dog and a ear of a tiger. All right. So why it is doing that is because the fully connected layer, it is saying that within the classes there is a class already. In a fully connected layer, it's only looking for whether it's true or false.
okay.
Okay. So in now we are moving from a fully connected layer. We were going from a feed-forward neural network to a CNN. By adding the activation here, the fully connected layer is an activation that passes it out to the output layer. The difference is that this is a tensor. Here it's a matrix. So now let's look at YOLO. So the important thing to note is that there are multiple bounding boxes, all right, and then whether it is a object or not, and then finally optimizing the best bounding box for those regions. All right, so let's go through it slowly. So what YOLO does is that it breaks up the image into 16 by 16 grid. This is just 9 by 9. But what it does is that it goes 1 by 1 by 1 by 1 to check whether there is an object. So this is not the you only look once. This is not the you only look once yet. This is now trying to find the objects within the cell. So it's already detected the objects. It's already detected there is an object. Now it is trying to find the localization. So there are two things happening. One, it needs to classify the object. The other, it needs to find the location of the object in the big picture. All right. To do this, it has to take each cell and find out what are the objects that are in it. So that if you can see, there is a green here, which is this green 8 by 8 matrix, because there's 3 classes, 8 by 1 matrix, and then there is an orange here. All right. So now it is going to determine which one to calculate. For example, it's a 0 here. That means there is no object in here. So it will ignore this. Now, when it detects there's an object here, it will start to calculate this and will create an array of bounding boxes and then generate a tensor of all the various classes. So this output tensor will have the possibility of it having a bounding box in this cell based on the objects. So you'll have an object here, you'll have an object here, you'll have a bounding box here. So now we have a bunch of what is these predictions? These are predictions. So again, this is a sigmoid prediction where it's a 1 or 0 whether there is an object, which is done using a sigmoid output function. Then the box coordinates is used by, it's done by linear regression to find the best bounding box. It predicts the best bounding box, and then finally the class. All right. So you'll get something like this. So you see the blue is here, the orange is here, and the green is empty. So it doesn't calculate this. All right. Once you look at the mathematics, it'll make a bit more sense. So this is how it happens in slow motion. It starts to split the image in S by S grid.
Mr. Gana,
Yeah.
just now the array box means array box they will give you a vector matrices and okay.
Yeah.
Because try to each this the 9 by 9 3 by 3 grid, right? Then array box then will give you a set of vector matrices. Then the other box will give you a set of matrices. Then you will have this a dot product. Then we'll get the bounding box.
Yeah. But this number will make this 0.
Yeah.
Because if you see in the formula, we have this one when there is an object. If this is 1, then we consider the location. If this is 0, then this whole thing becomes 0. So it depends on what the prediction says, whether there is an object or no object. So we use all these values to determine the loss function. This is the loss function. So there are 2 parts to the loss function. One is the localization. That means finding the bounding box. Okay, and then this one does two things. It does the classification of that object. So again, we have to see whether there is an object. So here it works in the reverse. 1 if there is no object, and 0 if when there is an object. So it reverses the value to nullify the confidence. So this is a confidence. So I will come back to that. So basically what we are doing now is we are drawing a bounding box. We are going through cell by cell by cell, all right? And this is done by the CNN, and then it starts to generate possible bounding boxes for each one. Now we do a linear regression to find the best bounding box. That's the first one. Then we have regions to find the classes. So two things are happening: bounding box plus the confidence and the class probability. Then only we get this. Okay, so this is the method employed by YOLO. You only look once. Sorry, I got a bit distracted because the results for the last exam just came out.
How did they do?
Only 6 pass out of 16.
Walao.
But one girl, Nazura, passed. I'm so glad she passed. Nur Hidayah failed the second time. Oh. This is quite sad actually.
How did Scott and some do?
They passed. Sam, Faisal, Scott, Durga, Nazura, Uwais passed.
Okay, that's good to hear.
So Mr. Gana, this passes is the first attempt pass.
No, one girl did twice already.
Oh.
Mohana did twice. Adam twice. Nur Hidayat twice. Yeah. So
Most of
Means
them,
that your best 3 class, most of them failed the first time lah.
actually the passing has been very small. I have to go back and look at the numbers. Ayo. Whenever the students go for exam, I am tension.
most of them score which part? The first, second, or third part?
I think all of them did badly in the exam now.
Oh, okay.
I'm sorry, in the coding.
Oh, okay.
Let me just check.
Same. Ayun.
See, all of them, one guy got 56%. Oh my God.
Mr. Kanna, 56, no lenient one.
Sure.
4 points only. Huh? 56. This is not, this was passing national exam. This to work.
Yeah, okay. So guys, you have to I don't know what to say lah. But the good part is that whatever we are doing here won't come out in the exam. Only the YOLO part will come out in the exam. The others, UNET, the image segmentation, face detection, all won't come out in the exam. But I have to say that the students who did put in a lot of effort for the capstone project actually did well. My passing rate has gone down again.
So overall, what's your passing rate?
It's about 40% only.
Oh, okay.
Okay, can I just take like a 10-minute break and see you all at 12 o'clock? I think after this, we will just go through this fairly quickly. I'll send you all, I will upload some articles for you all to read so you can understand better.
Okay, sure.
And please pay attention to YOLO, especially. I will send an article shortly.
Okay, sure.
Okay, sorry for the delay. Whatever it is, we have to move on. Okay. We need to crack this this exam thingy. All right. So please bear with me if I give you a bit more work than the usual. I don't know what else to do, but I think that the students that actually passed, there was one student who um, who actually didn't do very well in the class, but she managed to do well this time, Nazura. And she really put in a lot of effort, and she did well. She got 95 in the essay. She got 65 in the coding. So overall passing was 65%. So I think what also pulled them down was their essay questions. All right, so oh, yo, Huzaifa only got 56. Damn. Oh my God, one guy got 58. My God, also close. Okay, let's get back to you guys. I don't want to make the same mistake again. So yeah, I may extend class a little bit today. Okay, I hope you don't mind. So coming back to calculating how big the matrix is, the tensor flow that is being generated in this example. 7 by 7, you know what that is, right? That is your number of classes, and then given your confidence, your x and y height, and then your basically this is how we calculate the matrix that is going to be generated as an output. So there is a formula, and the formula is the grid row, grid column, which is 7 by 7, grid row, grid column, followed by the number of boxes, and then multiplied by the probability of an object, which is 1, and then the bounding coordinates, because we have 4 coordinates, x, y, h, and w, so it's 4, and then plus the 20 classes that could be any of the output. So whenever we say the shape, we actually talk about the shape like this 7730 for a YOLO output tensor. All right, this may come out in your objective question. All right, and it's important to understand how to generate this number. You just need to remember this formula right here. I have shared an article on the CN for you to read and understand what YOLO is. The most important thing about this article is, let me just pull it up shortly. All right. This is the first paper written about YOLO. Because YOLO has actually improved quite a bit. So YOLO is in a very quick explanation. YOLO is very quick to identify what is an object and what is not an object. It's a unified architecture, extremely fast, and it's able to process 45 frames per second. Because of this, it is able to be used for real-time detection. And one of the things about YOLO is that it is very good at predicting if there is an object. So it's high precision. The precision is very high. But so it's if there is an object, it will detect it more accurately. So that is one of the reasons why YOLO is used, and it's fast. But it's got a problem. If there are too many objects inside the picture, it is not able to draw the bounding boxes accurately. So we need to use a different type of detector. So you need to have a combination between something that predicts fast and something that predicts more accurately, depending on the type of solution you want to. So there it says here, compared to the state-of-the-art detection systems, YOLO makes more localization errors but less likely to predict a false positive background. Localization errors is because there are too many objects, so it makes localization errors, but it correctly predicts if there's an object. So you can use YOLO in a very general term to see whether there is an object or there is no object. But if you want to really draw a bounding box, if there are multiple objects in the image, then you would need to use something else. So even if you don't have the patience to read through the entire article, which is, I don't know how many pages, 700 over pages, you can just read a few lines. The abstract is the most important, and please read on. It also talks about the RCNN and the use of region proposals as opposed to using YOLO for the entire image to train. You will see that this slide deck actually took from this paper. All right, and then they use things like simple things that you need to understand is like the linear regression. All right, it used sum squared error, SSM. I think it's
It's only 10 pages.
huh?
It's only 10 pages, right?
What is this?
This the number that from the journal pages. But it's only 10 pages.
Oh, okay. Starting is 799. Sorry,
Yeah.
I didn't realize that. It's only 10 pages, so it should be more readable. And yeah, so they actually talk about in greater detail, and the example that I gave you, the final prediction tensor is here, and then they give you the formula. S by S is the grid size, and then B is the bounding boxes multiplied by 5 plus 1 times the 4 plus 1 plus times the number of classes. And that's how you get the YOLO prediction. Then you will, this is not, Is this the network? Let me just go back to the slide deck. Okay, so from a mathematical point of view, this part, the top part here is designed for localization, and the bottom part here is designed for classification. So pay attention to what these formulas mean. This one can be a 1 or a 0. So if it's the confidence is then improved. So you must understand that this is no object. Okay, this is object, this is no object. Confidence. What is the confidence when there is no object? That means it's 1 when there is no object and 0 when there is an object. So it's the reverse. They do this to eliminate situations where they dampen it's a coefficient that is applied to the confidence object. So this is the predicted class and this is the actual class. So that's how they do the loss function. All right, so all the ones that have a hat on it is the predicted. Okay, and what doesn't have the hat on it is the actual class. So from your perspective, you will get a question like this, 1376. So you need to break it down and find out what are the objects, how many classes, what is the S by S grade, and then how many bounding boxes. They've already given you 2 bounding boxes, so you need to figure out what is going to be the answer. So in a very high level, advantages of is good for real-time processing because it's very fast. If you want specific, you can see in the article, it actually tells you 45 frames per second. And then predictions made on one single network can be trained end-to-end to improve accuracy. So what is meant by you only look once is because it's using one single network to detect all 3 different types of predictions, whether there is an object, what is the center of the object, and what is the class of the object. All of these 3 things is done once. So that is why it is called you only look once. It's not because it's done, it's not because there's no feed, there's no back propagation or anything like that. That's nonsense. Okay, there's always back propagation, and YOLO will always check based on its current prediction against the output. The disadvantages are difficulty to detect objects that are small or crowded, and we would need to use a different network if we wanted to do crowded objects. Okay. Now this is another object detector, and it's called SSD. All right, and it's got a different philosophy than YOLO. Okay. Later, we will talk about another network called RCNN. The R stands for region, and the region proposal network, but this one doesn't use a region proposal. It takes one single shot to detect multiple objects within the image. Okay, so it's SSD is much faster than the 2-shot region proposal networks. So RCNN is a region proposal network. So they are saying that a single shot detector is much faster than a region proposal. So after going through a certain number of convolutions for feature extraction, right, it will obtain a feature layer of size m by n. Right, this is the feature size, and a 3 by 3 convolution is applied on the feature. So after they find a bounding box, they apply a convolution to look at it, look at the feature map, and then they apply a convolution on the feature map to find the best location. So for each location, we got a number of bounding boxes. So these are the number of bounding boxes for each location. Then we compute the class scores for each bounding box. This is what the class scores for each bounding box is doing. So we use a convolutional network to take these bounding boxes and find out what is the class based on the features that's inside it. So that is the difference between CNN. That is the benefit of a CNN. It is able to extract features and do the classification of the features. So remember now, we are not talking about the features of the image. We are talking about the features that's within the bounding boxes that we've detected already. So it's a one level further as to the. So that's why you have first you have to do the bounding box detection. Then you start extracting features using the convolutional networks. So the convolutional networks actually start capturing, classifies the features. All right. So this is what we call a single shot multibox detection. Let me just go back a little bit. The 4 by 3 convolutional network. This is a 5 by 3. So this is a 4 by 3 convolutional network. And there are 4 bounding boxes, and each bounding box will have 4 classes. The 4 by 3 output will be a 38 by 38 by 4. If there are 20 classes, then the shape will be 38 by 38 by 4 by 21. So that becomes plus 1 bounding class. So this is the convolution layer. They don't have the numbers for the convolution layer. Actually, these convolution layers have numbers. There's convolution layer 7, 8, 9, and 10. Similar to other convolution layers. Where I think this is 19 by 19, 10 by 10, 5 by 5, 3 by 3 are here. 11, convolution layer 11, 10, 9, 8, and 7. So these are the 4 convolutional layers that are drawing the bounding boxes around the features right here. That's why it's going smaller and smaller. This convolution layer is fully connected. If you see, it's fully connected 6 and fully connected 7. So it is maintaining the size. Although they call it a fully connected layer, but it's outputting the same matrix size. So the convolution actually begins right here. So this part is actually extracting the bounding boxes, and this part here is classifying the bounding boxes. That's what's happening.
Mr. Kana,
Yeah.
when you say it's extracting the bounding boxes, it's not extracting the object features, right? It's just extracting the boxes in the image where the object is there.
So now, yeah, basically you're right. It's extracting the features that it has detected within this box, and now it's generating bounding boxes. Because what it got is a bunch of bounding boxes. Now it's generating the features and checking which one has got the best class. So which bounding box is classifying this the best? Because each bounding box, for example, each dotted line will generate a probability and the location. All right. So we want to compare which one is giving us the highest probability of class within this region. This is what we call regions. So the first part of the CCNN of the SSD is extracting the regions. Then after that, we start looking into that region, and remember what we are trying to solve here?
Finding the class.
Finding the class, but actually we are trying to improve on YOLO. See, YOLO has got a problem of determining the location of the particular object. It knows that there is an object, but it's not able to localize the object. So that is why they are using the SSD to improve on YOLO.
So it's like making two things. Number one, like localize the object, localize the features, and then number two, like the class as well.
No, localize comes, see, what I mean by localize is that it gets a bunch of bounding boxes. That is the localization. So we want to see which bounding box gives us the best class probability.
Okay.
So then we can say in confirm that the red is the best bounding box region. Okay, so that is what it says by extracting a feature map of the feature map.
All right.
So the concept is to rectify the problem that YOLO creates. So YOLO is not able to localize crowded images, but again, we will run into problems, but for the purpose of the course, I need to explain to you this, which is the region proposal, which is RCNN. Okay, so you've understood what YOLO is. Okay, now you've understood what SSD means does. Now we're going to look at region proposals. Okay, so region proposals is like this, where it creates regions, what is background, what is foreground, what is the image, and so on and so forth. Then this is it gets the input image and it starts to create a region proposal. So the algorithm automatically creates 2000 proposals for every image. Okay, you'll find that this method kind of slows it down, but it is able to detect well. All right, so let's look at RCNN. They call this the slow RCNN because there are faster versions that came out of it. So the first thing it does, it takes the input image and extracts about 2000 regions in that image. All right, and then it starts to classify each of those regions. Okay, this method this method seems to be able to capture, but it's a slow method, but it's able to capture different objects within the image. So it does a selective search and generates about 2000 boxes of possible objects. Then the second part, it uses the network to create a dimensional a feature. It uses the network to generate a feature for each box that is proposed. And usually the input image is about 227, 227. And then finally, it uses the SVM and NMS to suppress the boxes. So that's how it generally classifies the regions. So it is selectively generating 2000 and then using a CNN network to extract the features, and then using the machine learning methods of SVM to and NMS to localize and classify the images. So you see, object detection can be done in basically we've done it in 3 different ways. By looking for, we break the image into cells and then find whether there's an object in there. That's YOLO. Then in SSD, we generate the bounding boxes like this, and then we classify within the bounding boxes which is the best possibility of a bounding box. If you notice that sigmoid is a good function for that. It's like a linear regression, but for whether it is a box or not a box, it is an object or not an object. Finally, we have now this method which is called the RCNN, which actually selectively generates 2000 regions, and then it starts to use the CNN to extract features from these 2000 regions, and then it uses SVM to classify and NMS to localize. All right. So basically, what the difference is that NMS and the classification is done towards the end, and we are looking at the classifying the what is that, the features within the regions. Okay, so these are the key differences you need to take back from the differences in between the different networks. Okay, so now because there's 2000 regions, it's becoming slow, so that's why it's known as the slow RCNN. So they brought in another one called the fast RCNN. This network is an improvement of the RCNN and claims that it's 9 times faster. Okay. And it also gives a better accuracy and of maybe 4%, much better than the RCNN. Okay, how does it work? The network is 3 modules. The first one is the region proposal. Okay, the second one is the feature extractor, and finally is the classifier and the regressor or the regression. the first part is actually extracting regions of interest. The first part, okay. So previously we were selectively generating 2000 regions. Now we are doing what is that? You see, there's two lines that is going in. One is doing a deep level convolution and a ROI projection. So we are doing some sort of region selecting, but we are filtering out what is important and what is not important, and then pushing a subset through. So this is the where we are it's a little bit different. The input image is fed into the feature extractor, and then it outputs a feature map using the ROI polling layer. So the ROI polling layer, which is like a pyramid layer, it extracts the feature map for each proposal box. So we still have proposal boxes, but the bottom line is we don't have 2000 of them. All right. So for that reason, it is able to compute 29 times faster than the FCNN, RCNN, RCNN. All right. And then finally, it is put through a fully connected layer, which is doing the classification. And then there are two different outputs. Okay, this one you will start to see very common now. There are two outputs being copied to two separately different fully connected layers. One does the classes, one does the coordinates. Okay, so so the changes are now getting a little bit more subtle in terms of how we what is that we did for YOLO. So YOLO did all of this at once. Now we are actually forking it and then combining the results. All right, so so it's something for you to kind of take note of. I at first when I was trying to study this as well, it was sir, does RCNN classify all 2000 regions? Yes, but then what it does, it finds the best probability. So because it's got 2000 regions, it cannot take all 2000 regions. So it needs to find the best probability. That's why it does it checks the class with the highest probability to be the object in that region. So it goes through a process after it is generating the regions. So now in this fast RNN, we are trying to filter the regions before they get. So it's actually the filtering is either happening before or it's happening after. So you must understand, right? What is the complexity is that all these networks came after and after the other and the other and the other. So if you ask me now, after 5 years, these networks have been created. Why are they going back and forth, back and forth? Is because it is the same person or the same team that actually built RCNN that kept on rebuilding it and improving it until it is where it is right now. So that is why we are actually learning the history of how RCNN evolved from RCNN to faster RCNN. That is where we are at right now. So it's important to understand that we are at a point where we are looking backwards at history. You know, like when you look at the, I just want to digress a little bit. Just bear with me for a minute. Let's say if you were, when you were younger, in your, when you were going to school, right? You probably sat in a car that was manual drive, right? And then today you are driving a car that's automatic. So that knowledge of automatic didn't come by itself. We had to go through the whole process of driving it manually and then putting it on gear and then finally putting automatic transmission. So that is where we are at right now. So we start off with something we think that may solve the problem, but then after, when we look at it again, wait a minute, there's a way to change it, there's a way to improve it. So we keep moving the boundary. Okay, so that is what actually is happening with this RCNN. So you must understand, it's the same people that kept on building on it to accelerate its training, accelerate its accuracy, and then to get the network that we have today. So this won't come out in your exam, but you need to understand how machine learning, deep learning actually builds on itself. All right. So if you understand this ROI projection, you have to accept the fact that when you combine the neural network with ROI polling layer, it generates a smaller set of regions. That is what we want. Basically, a smaller set of regions that has an object in it. And then after that, we classify it, we classify the features, and we get a vector. And that vector is then, we do the normal, whether there is an object or whether there is a bounding box, and do the regression to get the final output. Because what we want is two things: whether there is an object and what is the position of the object. So these are the two things that the fully connected layer is responsible for. So you will find that the next network that we study is a shortcut that we take above, around this fast RCNN. So just to give you some statistics, it's 64 times faster than the RCNN when it roughly in terms of sampling one region, and it improves the training time and also processing of the batch size, rather than issuing new images for each region. Okay, now we shall go to the last network, all right, for today. So from the exam perspective, if they were to ask you, this is all you need to understand. Fast RCNN is significantly faster in training and testing sessions over RCNN. If you want, you can actually give them some numbers, how many times faster and so on it is. Okay. In the faster RCNN, there is also another slight improvement over fast RCNN. So there is this RPN that they are bringing in, called a region proposal network, which is actually a combination of the VGG and the ZFnet, instead of using selective search. All right. So the network again is made up of three parts. The first part is the convolution layer that is used to extract features from the image directly. The second part is a region proposal network used to generate the ROI. So now they are using another entire fast network. You remember VGG? VGG is a fast network where it's a very complex network and it'll go right through. So they are using the VGG to a VGG equivalent CNN to generate a region proposal network that is used by the classifier. So once they propose the region proposal network, the classifier for each region of interest, there is an object from the target class. So that's how they generate. So this region proposal network generates the proposals, and then they use a classifier to classify it, and then they map the feature maps on top together. So there is some sort of concatenation here to generate the ROI polling for each region. So you can see that there is a region proposal network and there is the fast RCNN, and this output is then put back into this this part of the fast RCNN. So if you recall, this is similar to a VGG where it is a very complex CNN, but it's because it's got the polling layers, it's able to go pass right through. Remember, the one by one matrix allows it to go pretty fast. So what is output here is then added on to this particular output. All right, and then this is the region proposals, regions of interest, which is then added to the feature map, and then now we start classifying the regions of interest to get the best output. So this adding this particular VGG equivalent or ZFnet equivalent actually allows us to generate object proposals. That is what they are trying to say. Instead of, what they mean by object is actually a matrix of the proposals that's instead of a region covering a larger area, now they are actually zooming into a particular object to define the bounding box for them to do the regression and the softmax. All right, so you will find that they just keep doing the same thing over and over again, different ways, one from the front, one from the back, and so on and so forth, to get better accuracy. And you can see how it has drastically improved as you go down the networks, right? So I just feel that it's a pain in the butt to actually remember all of this. Even this slide, I don't think is descriptive enough. By the way, SkyMind came back and said that that slide is a mistake. All right, so they have asked they will update the slide deck. All right, so thanks for pointing it out. Okay. Okay. Okay, I suddenly feel so much better because the SkyMind guys are saying that my students are performing better than their students. So this is I'm quite happy actually. Anyway, just to digress. Yeah.
Congratulations.
Yeah. Thanks. I mean, that's a huge statement coming from them. So,
Mr. Kana being said that, then our success rate is 30% to 40%. This is also very alarming.
Hey, you know, when I took the exam, only 3 people passed, you know, out of a class of 17 people.
Oh.
Out of a class of 17 people, only 3 passed.
Very scary lah, boss.
When they say the sky mine passing rate low, I mean, are those their intern or what?
No, SkyMine is doing training for a lot of universities. University Science Malaysia, UKM, they're doing training for a few companies. So they are also doing training directly.
Okay.
And they are also training, master's students, they are training PhD students. We are only doing fresh graduates.
Okay, understand.
So you know.
Yeah.
Anyway, okay, so let's just clean up this slide deck. And then after this, you guys can actually just have a look at. So from a practitioner point of view, right, we want you to understand where YOLO is sitting, where fast RNN is sitting, where SSD is sitting, and where faster RCNN is sitting. So you need to understand which algorithm to use. Make sense? Don't worry, if you say yes, I'm not going to say you know. I'm just going to say that whatever we have talked about today is a very high level discussion about the network, and all you need to know is how it performs and a little bit about the structure, so you'll be able to understand, sir, how to define small, medium, large objects. Tam, I don't know how to answer that question. I guess it's by the. Actually, there's no small, medium, large objects. There is either many objects or there are few objects. Because YOLO fails when there are many objects. RCNN is better when there are many objects. Okay, so basically we want you to understand. Oh, you're referring to this diagram here. Okay. Okay, this diagram is old because it's ending in 2029. We should have something. Okay, this is. We should have 2020 and moving forward. I think there are a few more things that they need to add. I saw the new slide deck. It's not changed. It's the same thing. So I'll ask them why. Okay. And basically, this is the accuracy of the network. So you can see this is the GPU time, and this is the mean average precision that they measure how well it's able to detect. All right. So remember the inception model, the Google ANET. So that's the inception model. They have the V, the version 2, version 3, This is an inclusion of the ResNet as well. Then you got the plain vanilla ResNet. Then you got the VGG. So all this is just talking about object detection. Okay. So please understand where we are coming from, what we want you to understand, and so on and so forth. It's the same thing that we need to do in object detection. Object detection has got two problems. One is to detect the object. Second is to detect the location of the object. So combining these two together, I'm able to detect whether there is an object to understand my outside world. But how we do it, we can do it in many ways.